Hello and welcome to another lecture of classical motion of a single particle. This is going to be the last week of this course, and in this week I will mostly cover some interesting topics of nonlinear dynamics, and this week I will also tell something which is a little bit advanced maybe with respect to the general or average level of this course, but this will be somehow giving you some exposure to the general aspect of nonlinear dynamics. But before that, I will somehow continue our discussion, our previous discussion on the general dynamics in a two-dimensional phase space. So, if you remember that in 2D phase space, the evolution equations for the two state variables x and y, they are simply written in a most general way as this when we are considering linear systems. Okay. So, these are the general form of linear systems in 2D phase space or flow. Okay. Now, if I write like this, then I can again say that I can define a vector which is consisting of the coordinates in the phase space, okay, and I can also define a vector which is consisting the velocities in the phase space, okay, which is given by x dot. So, this is phase space velocity vector, and this is phase space coordinate. Okay. And we have now x dot is equal to, which is nothing but equivalent to dx dt is equal to a times x vector itself, where this a is given by a 2 by 2 matrix. And for us, we know that this is simply equal to a, b, c and d. Okay. Now, today first I will show you a general theorem. So, if this a vector, this a matrix has eigenpairs lambda and v, that means this is the eigenvalue and this is the corresponding eigenvector, okay, then it can be shown that, so I simply write if a matrix has eigenpairs like this, then e to the lambda t times v is a solution of, if I number this equation as equation number 1 of 1. Okay. How to show that? So, the proof is pretty simple. You can simply check that whether x is equal to this satisfies this equation or not. So, if x is equal to e to the power lambda t times v, then dx dt will be equal to, so you know that this is just the eigenvector which does not contain any time here. Okay. This is consisting, this is a function of the phase space coordinates. Okay. So, the only time dependence comes from this term. So, it will be lambda times e to the power lambda t times v, okay. And I can, lambda is just a number. So, I can write e to the power lambda t lambda times v. Okay. Now, lambda times v by definition is equal to a times v. Okay. That is the definition from the here. If lambda and v are respectively the eigenvalues and the eigenvectors of A, then I can write A v is equal to lambda v. Okay. That I am actually using over here. This lambda v will now be replaced by A v. E to the power lambda t is finally is a number, and so is a scalar. So, it will simply be multiplied to the vector itself just like this, e to the power lambda t times v. Okay. And then you see that if you start by saying that dx dt is equal to this, and that will finally gives you through all these steps is equal to a to the a times x. So, basically this is a solution of an equation which is looking like dx dt equal to a times x. Okay. Why it is important? Because you see sometimes, as we saw in some previous examples, you had to integrate, okay, directly right from the equations. For example, x dot equal to x or y dot equal to y, you had to integrate to find the solutions. Here actually you can directly find the solution just by using this theorem. Another interesting theorem, I mean another interesting conclusion, okay, analytical result is now, and that we will actually use very frequently in the following discussion. That is, let us say I have another important and interesting analytical result is this: x dot is equal to ax plus by, y dot equal to cx plus dy, and from that what we can do, we can take the another dot on both sides of each equation, and we can find x double dot is equal to ax dot plus by dot, and for this equation I can find y double dot is equal to cx dot plus dy dot. Okay. Again, you can also write from this equation cx dot is equal to cax plus cby, and from this equation you can write ay dot equal to acx plus ady. You can subtract one from the other, and then you will have cx dot minus ay dot will be equal to bc minus ady. Okay. And so, you can also write cx dot is equal to ay dot plus bc minus ad times y. Okay. Now, you know this expression, and you can put this in this expression for y dot, y double dot. So, it will now be, I can write y double dot will now be equal to ay dot plus bc minus ady plus dy dot. And finally, we can write for y the resulting equation to be equal to y double dot minus a plus dy dot, okay, plus ad minus bc y is equal to 0. Similarly, one can also obtain x double dot minus a plus dx dot plus ad minus bc x equal to 0. Okay. This I personally request you to check, okay, and you will find that both x and y they are satisfying the same equation. Now, what is the message from that? The message is that if you now see what a plus d is and what ad minus bc is. So, you have the matrix A which is given by A, B, C, D. So, A and D, when they are summed up, they give you the trace, okay. So, of trace of A. So, I can write now we observe that trace of A is equal to A plus D, and what is determinant of A? That is AD minus BC. So, the final equations for x and y will be x double dot minus trace of A times x dot plus det of A, determinant of A times x is equal to 0, and y double dot minus trace of A y dot plus det A times y is equal to 0. Okay. You have two similar equations, okay, one for y and one for x. Now, of course, if you do, you understand this form, that is great, and now I am just going again to this form. I am just now saying that this is a simple, this is a second order linear ordinary differential equation in x, and this is also a second order ordinary differential equation in y. Okay. So, this type of thing whenever I have with constant coefficients, okay, that is very important, then we can have solutions like this. So, x is equal to, I can think of some x 0 e to the power lambda t, okay. And if I do that, then can be taken as a trial solution, okay. And then we have so lambda square minus a plus d lambda plus AD minus BC is equal to 0. Okay. Same thing is obtained from the equation of y. Okay. Now, again, or lambda square minus trace of A times lambda plus det or A is equal to 0. Okay. So, it means that if lambda has two roots, lambda 1 and lambda 2, then lambda 1 plus lambda 2 will be equal to trace of A, and lambda 1 lambda 2 will be equal to determinant of A. Okay. And this is exactly saying you that lambda 1 and lambda 2, they are nothing but the eigen values of the matrix A, capital A. Okay. So, it means that then the general solution of x can be written as, I can say, like some alpha, okay, e to the power, okay, lambda t lambda 1 t plus beta e to the power lambda 2 t. Okay. Similarly, for y I can write, it is a different constant of course, gamma e to the power lambda 1 t plus delta e to the power lambda 2 t. Okay. Now, you see that by this result you have a clear cut way to find or to write the total solution, the general solution for x and y, for each of the phase space coordinates, okay, for a given linearized system. Okay. Thank you very much.